You know what fire is, right? Sure you do. Everybody does. You have known what fire is since you were 3 years old. Hot, bright, dangerous. It burns things. It makes light. You can cook with it, warm your hands by it, and if you touch it, it hurts. Fire. Simple. That is completely wrong, and I can prove it. See, I want you to try something right now. I want you to tell me what fire is, not what it does, not what it looks like, what it is. You say it is hot? Fine. Lots of things are hot. A radiator is hot. Soup is hot. The inside of your car in August is hot. Those things are not fire. You say it is bright. Also fine. A light bulb is bright. The sun is bright. A firefly is bright. Not fire. You say it burns things. Getting warmer, if you will excuse the pun. But burning is what fire does. That is a verb. I asked you for a noun. I asked what fire is. And if you really sit with that question, if you really try to pin it down, you find something uncomfortable, something genuinely disturbing. If you think about it long enough, you cannot point at fire the way you point at a rock or a glass of water or a piece of steel. A rock is a thing. You can pick it up. You can weigh it. You can put it on a shelf and come back tomorrow and it is still there. Water is a thing. Steel is a thing. But fire is not a thing at all. Fire is something that happens. It is an event, a process. And what that process actually involves when you look at it with honest eyes and a willingness to be confused is so much stranger and more beautiful than anything you were told in school. Let me start with a very simple observation, something so obvious that most people walk right past it without noticing that it is extraordinary. You take a log, a nice dry log sitting in your fireplace. It has been sitting there for hours, days, weeks, maybe if you have not used your fireplace in a while. The air is all around it. The oxygen in the air is right there, brushing up against the surface of the wood constantly. Oxygen molecules are zipping around at hundreds of meters ass, slamming into that log thousands and thousands of times every second, and nothing happens. Absolutely nothing. The log just sits there. The oxygen just sits there. They are like two old friends who forgot they know each other, but then you strike a match. You hold that little flame to the corner of the log. You wait a moment, something catches, and once it catches, it does not need the match anymore. It feeds itself, it spreads, it grows. And eventually the whole log is consumed, turned to ash, and the energy comes pouring out as heat and light. Why? What changed? The oxygen was always there. The wood was always there. Every ingredient was present the entire time. What did the match actually do? This is the first crack in the idea that fire is simple. Because if fire were merely wood plus oxygen equals flame, then every piece of wood on earth should be on fire right now. Every tree in every forest, every wooden house, every telephone pole, every fence post, every pencil on your desk should be blazing. The air is roughly 21% oxygen. There's fuel everywhere. So why is the world not an inferno? The answer has to do with a hill, not a real hill, an energy hill. Think of it this way. Imagine you have a ball sitting on a high plateau, and at the edge of the plateau, there is a little ridge, little bump, like a speed bump on a road. On the other side of that bump, the ground drops away into a deep, deep valley far below. The ball is sitting on the plateau, perfectly content. It would love to roll down into that valley. There is a tremendous amount of energy to be released if it could get there, but it cannot because of that little bump. The ball does not have enough energy to get itself over the ridge, so it just sits. Now imagine somebody comes along and gives the ball a little push, just enough to nudge it over the bump. And then what happens? It rolls down the slope. It picks up speed. It goes faster and faster as it drops into the valley. All that potential energy converts to motion. And when it reaches the bottom, it has released an enormous amount of energy, far more than the tiny push that started it. That is exactly the situation with your log and the oxygen in the air. The carbon atoms in the wood and the oxygen molecules in the air have a tremendous affinity for each other. They desperately want to combine. When carbon and oxygen do get together, they form carbon dioxide. An enormous amount of energy comes flying out, but there is a barrier. Chemists call it the activation energy. At room temperature, the atoms are not jiggling hard enough, not moving fast enough to get over that barrier. They bounce off each other and go their separate ways. Nothing happens, and that is what the match does. The match is the little push. It provides a concentrated burst of heat right at one spot that makes the atoms in that spot jiggle violently enough to shove a few of them over the energy hill. And when those first few carbon atoms find their oxygen partners and snap together, they release energy, a lot of energy. And that released energy makes the neighboring atoms jiggle harder, hard enough to get over their hills. And those atoms release energy too, which pushes the next batch over. And the next and the next. It is a chain reaction, a cascade, a domino run made of atoms. One tiny match, one little push starts a process that sustains itself, that amplifies itself, that grows and grows until the fuel is used up. That is why fire spreads. That is why a single spark can burn down a forest. Not because the spark has a lot of energy. It has almost no energy at all. But because the spark triggers a release of energy that was already there, locked inside the wood, waiting. By the way, this is why different materials catch fire at different temperatures. Paper catches easily. You barely have to try because the energy hill for paper is low. The molecules are simpler. The barrier is smaller. And a tiny amount of heat pushes them over. Wood takes more effort. You need sustained heat. A match held in place for several seconds because the hill is taller and something like iron. You can heat iron in a forge until it glows red and it will not burn in ordinary air. The hill is enormous. But get iron hot enough or grind it into a fine powder so the surface area is huge and even iron will burn spectacularly. In fact, steel wool touched to a flame showers sparks like a firework. Same iron, same oxygen, same reaction, just a different approach to the hill. So the energy barrier is not just a curiosity, it is the reason the world is habitable. If there were no activation energy, if carbon and oxygen could snap together freely at any temperature, then every piece of organic matter on the planet would have burned ages ago. Life would be impossible. The activation energy barrier is a dam holding back a flood of chemical energy. It keeps the world from spontaneously combusting, and matches, lighters, sparks, friction, lightning, these are tiny controlled breaches in that dam. And notice something else. Once the chain reaction is going, you do not need the match anymore. You can blow the match out. The fire keeps burning on its own because the reaction produces more than enough heat to keep pushing new atoms over the hill. This is what we mean when we say fire is self-sustaining. It is a process that creates the conditions for its own continuation, like a rumor spreading through a crowd. One person tells two people, those two people each tell two more, and before long the whole room knows. The original gossip could leave the party and it would make no difference. So already we have learned something important. Fire is not a substance, it is a self-sustaining chemical chain reaction. Good. But that only opens the next question, and this one is even more interesting. We see the light, we see the beautiful orange and yellow glow of a flame. Where is that light coming from? What physically is doing the glowing? Most people will say the gas is glowing, hot gas, and that sounds perfectly reasonable. Heat up a gas, it glows like a neon sign, like lightning. But if that were the whole explanation, then every flame would look like the flame on a Bunsen burner in a chemistry laboratory. Have you ever seen a Bunsen burner running with the air intake wide open? The flame is almost invisible, a pale blue shimmer. You can barely see it in a well-lit room. And here is what makes it puzzling. That blue flame is actually hotter than the orange flame of a candle, much hotter, yet it produces almost no visible light. Just a few blue wavelengths from excited molecular fragments called radicals, that is it. So where does the rich, warm orange light of a campfire come from? It comes from something you would never guess. It comes from dirt. Well, not exactly dirt, it comes from soot. Though when wood burns, the heat is ferocious. It tears apart the complex organic molecules in the wood. Big tangled chains of carbon, hydrogen, and oxygen get ripped to pieces. Carbon atoms get shaken loose. Now, some of those carbon atoms find oxygen partners right away and combine into carbon dioxide. Job done. But many others are not so fortunate. They do not find oxygen quickly enough. Instead, they cluster together into tiny, tiny solid particles, microscopic lumps of carbon. So these particles are unbelievably small, far smaller than the width of a human hair, smaller than a wavelength of visible light in some cases. And there are millions upon millions of them swirling and tumbling in the hot gas of the flame. And here's the key. These are solid particles, not gas, solid. And when you heat a solid to very high temperatures, it glows. This is a fundamental principle of physics called black body radiation. Any solid object at all, a brick, a piece of iron, a grain of sand, if you heat it hot enough, it will begin to emit light. First, a dull, deep red, the kind of red you see in the coals at the bottom of a fire, then brighter red, then orange, then yellow, then if you push the temperature high enough, brilliant white. The hotter the object, the shorter the wavelength of the peak light it emits. This is why a piece of steel in a blacksmith's forge starts red and turns orange and then yellow as it gets hotter. The color is a thermometer, and those tiny soot particles in a candle flame or a wood fire, they are heated to roughly 1,000 to 500 degrees or more. At that temperature, they glow orange and yellow, that beautiful warm firelight that humans have gathered around for 250,000 years since our earliest ancestors huddled in limestone caves, is the glow of tiny solid particles of half-burned carbon floating upward on a column of hot gas. This is the same physics as an incandescent light bulb. By the way, you run electricity through a thin tungsten filament. The filament heats up and it glows. Same principle. A light bulb and a candle are doing essentially the same thing, heating a solid until it radiates visible light. And this reveals something wonderful and slightly ironic. The very thing that makes a campfire beautiful, that gorgeous warm orange glow, is a sign that the burning is incomplete, sloppy, wasteful. The carbon did not finish its job. It got partway through the reaction and stalled out, floating upward as soot, glowing with the energy it absorbed, but did not fully release. A perfect flame, a flame where every carbon atom successfully combines with oxygen and burns completely, would be nearly invisible, blue and faint and efficient and frankly boring to look at. That is why a gas stove burns with that pale blue ring. The gas is pre-mixed with air. The oxygen supply is abundant. Combustion is nearly complete, and there is almost no soot. No soot, no orange glow, just blue shimmer. Perfection in the world of combustion is almost invisible. Beauty is imperfection made incandescent. Fireworks, by the way, are an entirely different trick. When you see green fire or red fire or blue fire in a fireworks display, that is not blackbody radiation at all. That is something else. Different metal elements, when heated, emit light at very specific wavelengths. Copper compounds give you blue-green. Strontium gives you red. Barium gives you green. Sodium gives you that deep orange-yellow. The same color you see when you spill salt into a campfire, and the flame turns a vivid yellow-orange. These are atomic fingerprints. Each element has its own signature color, determined by the energy levels of its electrons. The electron gets excited, jumps up to a higher energy state, and when it falls back down, it emits a photon of a very precise wavelength, very precise color. It is beautiful physics, and it is completely different from the black body glow of soot. Two different mechanisms of light production happening in the same campfire side by side, and most people never realize they are seeing two kinds of light at once. All right, so fire is a chain reaction, and the light comes from incandescent soot particles acting as tiny black body radiators. Interesting, but we have not reached the deepest part yet, not even close. The deepest part is this. Where does the energy actually come from? When you burn a log and all that heat and light pour out, where was that energy hiding before you struck the match? To answer that, I want to tell you about a fellow named Jan Baptista van Helmont, a Flemish physician born in 1580. And he had a question that nobody in his era had tried to answer carefully. Where does a tree come from? Not philosophically, physically. What is a tree made of, and where did that material originate? Sounds like a foolish question. Trees grow out of the ground. Obviously, they start as seeds in the soil. They push roots down into the earth, and over the years they grow tall and thick. The answer seemed obvious. Trees come from the dirt. They eat the soil. Van Helmont did not trust the obvious answer. So around 1620, he set up one of the most elegant experiments in the history of science. He took a willow sapling. He weighed it carefully, 5 lb. He took 200 lb of soil, dried it in an oven so he knew the exact weight, and packed it into a large earthen pot. He planted the sapling. He covered the top of the pot with a perforated metal plate to prevent any dirt or dust from blowing in from outside. And then for 5 years, he watered the tree with nothing but rain water or distilled water, nothing else, just water. 5 years, he waited 5 patient years. At the end, he pulled out the tree and weighed it, and 169 lbs. The tree had gained 164 pounds. Then he dried the soil again and weighed it. It had lost only about 2 Oz out of 200 lb. The tree gained 164 lbs of solid wood, bark, and root, and the soil was barely touched. Van Helmont concluded that the tree must have come from the water. He was wrong about that, but magnificently wrong. He was asking the right question in the right way. And the real answer, which would not be understood for another 2 centuries, is more astonishing than anything he could have dreamed. The tree came from the air. Let me say that again because it sounds insane. The solid, hard, heavy material of a tree, the stuff you can knock on with your fist, the stuff that holds up a house, is made primarily of carbon. And that carbon did not come from the soil. It came from carbon dioxide in the atmosphere. The tree pulled it in through tiny pores in its leaves, ripped the carbon away from the oxygen, used the carbon to build its body, and released the oxygen back into the air as a waste product. That process is photosynthesis. And the energy needed to do it, the energy required to tear carbon away from oxygen against their powerful natural attraction, came from one place: sunlight. A tree is a machine that runs on starlight. It takes energy from a star 93 million miles away and uses that energy to drag atoms apart and rearrange them into wood. It is pushing the ball up the hill slowly, patiently, over years and decades, storing energy in the precise arrangement of atoms. The sun provides the force, the tree stores the result. Every growth ring you count in a cross-section of a trunk is a year of sunlight recorded in carbon. So when you look at a piece of wood, What you are really looking at is solidified air and trapped sunshine. That is not a metaphor, that is a description of the actual physics. The carbon came from the air, the energy holding it in that configuration came from the sun. Wood is air and sunlight made solid, and now the whole picture snaps into focus. You take that piece of wood and put it in your fireplace. You strike a match, and what are you doing? You are reversing what the sun did. You are letting the carbon rush back to the oxygen it was separated from. You are letting the ball roll back down the hill that the sun spent years pushing it up, and the energy that comes flooding out the heat and the light of the fire is the heat and the light of the sun that went in. It was stored, it was patient. Locked inside the molecular structure of the wood like money in a vault, the match was the key. When you sit by a fire on a cold winter night and feel that warmth on your face, you are feeling the warmth of sunlight that fell on green leaves years ago, maybe decades ago. Sunlight that was captured by chlorophyll, converted into chemical energy, packed into carbon bonds, stacked as cordwood by the back door, now released into your living room. The fire is not creating energy, it is returning energy. It is letting the sun out of the tree. A fireplace is a kind of time machine for sunlight. The photons warming your hands are not the same photons that hit the leaf. Of course, the energy has been transformed several times over from light to chemical bonds to heat and light again, but the amount is conserved. Not a scrap is lost or created. What the sun put in, the fire gives back, and the story reaches much, much further back. Coal is ancient trees, ancient ferns, ancient swamp plants that lived and photosynthesized roughly 300 million years ago during the Carboniferous period. They captured sunlight, died, were buried under sediment, compressed by geological forces over vast spans of time, and slowly transformed into coal. When you burn coal, you are releasing sunlight from 300 million years in the past. You are warming your hands by the glow of a star that shone on forest before anything with a backbone walked on land. Oil and natural gas are the remains of ancient marine organisms, tiny creatures that floated in shallow seas, capturing energy from the sun through their own small lives. They died, drifted to the bottom, were buried, and over hundreds of millions of years were cooked by heat and pressure into hydrocarbons. When you turn the key in your car and the engine catches, you are detonating ancient sunlight measured in careful little explosions thousands of times a minute. Every fire that humans have ever lit, every campfire, every furnace, every candle, every engine, every rocket has been powered by the same thing. Stored starlight, the sun does the work of pulling atoms apart. Biology stores the result. Chemistry lets it snap back together. And physics describes the entire beautiful cycle from start to finish. There is one more piece of this story, and it is the piece that tends to make people very quiet when they hear it for the first time. When a tree grows, it pulls carbon dioxide from the air and releases oxygen. When the tree burns, it takes in oxygen and releases carbon dioxide. The chemistry of burning is the chemistry of growth, running in reverse. Atom for atom, bond for bond. Fire is ungrowing. Fire is photosynthesis played backward. Everything the sun spent years carefully assembling, fire disassembles in an afternoon. And you can push this thought further and it still holds true. You are burning fuel right now inside your body. Every cell you possess is running a slow, exquisitely controlled version of the same chemical reaction. The food you eat, the sugars in your bread, the fats in your butter, the starches in your rice, these are carbon-based molecules assembled by living things using energy that ultimately traces back to the sun. Your body takes those molecules, combines them with the oxygen you breathe in, and extracts the stored energy to run your muscles, fire your neurons, pump your blood, maintain your body temperature at roughly 98.6 degrees F. What do you exhale? Carbon dioxide and water vapor, exactly what a wood fire produces. You are, in a very real and literal chemical sense, burning. You are a slow, carefully regulated fire. Your body heat, that warmth you feel when you press your hand against your own skin, is the heat of controlled combustion. The same fundamental reaction that lights a campfire is keeping you alive right now, just managed with extraordinary precision by enzymes that evolution spent billions of years perfecting. And think about what happens when you exercise hard. You breathe faster. Why? Because you need more oxygen. For what? For burning. Your muscles are burning sugar faster, demanding more oxygen to keep the reaction going, producing more carbon dioxide that you have to exhale. When you get out of breath running upstairs, you are experiencing the exact same bottleneck as a campfire being smothered. Not enough oxygen to sustain the rate of combustion. When you eat breakfast in the morning, you are loading fuel. When you breathe, you are fanning the flames. When you feel warm, you are glowing just too faintly for your eyes to see, but an infrared camera picks it up clearly. You are radiating heat constantly the way any warm object does. You are a fire that eats cereal and reads the newspaper. So here we are. We started with something everybody thought they understood, something so familiar it seemed beneath examination. Fire, just fire. And it turned out to be a window into the deepest patterns of the natural world. Energy flowing from the sun across 93 million miles of vacuum, captured by leaves thinner than paper, locked into the structure of wood for years or centuries or hundreds of millions of years, and released in a rush of heat and light when the atoms finally find their way back to each other. Fire connects the sun to the leaf to the wood to the hearth to the warmth on your face. It connects photosynthesis to digestion, plants to animals, biology to chemistry, chemistry to physics, the living to the non-living, the present to the deep past in one unbroken chain of energy flowing through the universe. So the next time you sit by a fire, whether it is a campfire in the woods, a candle on a dinner table, or just a match struck in a dark room, I want you to really look at it. I want you to see the soot particles glowing like billions of tiny furnaces. I want you to see the carbon atoms reuniting with oxygen after being held apart by sunlight for years. I want you to feel the activation energy hill and the chain reaction cascading over it. And most of all, I want you to see the sunlight coming back out, because once you see that, truly see it, you will never unsee it. And a candle flame will never be ordinary again. People ask me, what is the point of knowing this? I could enjoy a fire just fine before I understood any of it. Sure, you could, but you are enjoying the surface, the warmth and the color and the crackle. When you understand what fire really is, you are seeing the inner machinery of the universe exposed right there in your living room. You are watching sunlight from years past cycle through matter according to laws that have held since the beginning of everything we can measure. That does not diminish the beauty. That is the beauty, the deeper kind, the kind that makes you go quiet inside and does not wear off. The world is not what it looks like. It never has been. The simplest things, the things you thought you understood when you were 5 years old, fire, trees, air, light, your own breath, these are the things that hide the deepest secrets, and you just have to be willing to ask the question that everyone else stopped asking a long time ago. What is fire really? Now, you know it is the sun. It was always the sun. I'm curious. What is the most ordinary thing in your daily life that you have stopped and realized you truly do not understand? Think about it. I promise you the answer is stranger and more wonderful than you.